Hello, everyone. Today, we will discuss Section 2 of Chapter 4, CFT Consensus Algorithms. CFT, or fault tolerance, is a fault-tolerant technology for non-Byzantine problems. CFT consensus algorithms address scenarios in distributed systems where faults exist, but there are no malicious nodes. These algorithms deal with issues such as message loss or duplication, but they assume no erroneous messages, focusing on how consensus is reached in such situations. This is one of the most common problems in the field of distributed consensus, also known as the Paxos problem. It was first described by Leslie Lamport using the pencil and paper story model, which is how it came to be named. The algorithms that solve the Paxos problem mainly include the Paxos series and the Raft algorithm. Both the Paxos algorithm and the Raft algorithm are considered strong consistency algorithms. For distributed networks, nodes often face issues like network interruptions, node failures, or even being illegally infiltrated and having messages forged. The problems encountered by nodes can be categorized as follows. 1. Non-Byzantine errors, meaning a node has failed but does not forge information. 2. Byzantine errors, where a node may forge malicious responses. Nodes that forge messages are called Byzantine nodes. Correspondingly, consensus algorithms can be divided into CFT and BFT categories. CFT algorithms only tolerate node failures, but do not tolerate nodes acting maliciously, while BFT algorithms can tolerate both node failures and malicious node behavior. As mentioned earlier, Paxos is a CFT consensus mechanism. The Paxos algorithm includes three main participants. The proposer, who submits proposals, which are represented as value, N, where value represents the proposed value and N represents the proposal number. The acceptor, who accepts a proposal and, upon acceptance, considers the value of the proposal to be finalized. The learner, who is informed about which values have been selected and then considers that value to be chosen. In the Paxos algorithm, with the model of N equals F plus 1, it can tolerate F failed nodes. The main process is as follows. Phase 1. The proposer selects a proposal number N and sends a prepare message with number N to more than half of the acceptors in the network. If an acceptor receives a prepare request with number N, and N is greater than the highest numbered prepare request the acceptor has already responded to, it will return a promise message to the proposer. This message includes the highest numbered proposal the acceptor has already accepted, and the acceptor promises not to accept any proposal with a number smaller than N. Phase 2. If the proposer receives responses from more than half of the acceptors to the prepare request with number N, it will send an accept request for the value, N, proposal to more than half of the acceptors, where V is the value of the highest numbered proposal from the received responses. If no proposals are included in the responses, the proposer itself will decide the value V. If an acceptor receives an accept request for a proposal with number N and has not responded to any request with a higher number, it will accept the proposal and return an accepted message. Next, let's look at the Raft mechanism. Raft is based on common safety issues in distributed systems, such as failures occurring in some nodes of the system due to certain reasons. The Raft protocol's proper operation requires that at least half of the nodes in the system must function properly. Therefore, Raft primarily involves two processes: election and log replication. In Raft, each node can have one of three roles, and the roles can transition between each other: follower, candidate, or leader. The Raft mechanism is implemented in two stages. the election stage, and the log replication stage. Other types of CFT consensus algorithms include Paxos, Multi-Paxos, and Raft. Alright, everyone, that concludes Section 2 of Chapter 4.